Hi, welcome back to our lecture on a practical guide to quantitative finance interviews. This is our 12th lecture, and today we are going to talk about distributions, which I think is one of the quite fundamental probability for the probability theory. And we are going to review a variety of them for random variables, which are widely used in quantitative modeling and trading. So although it may not be necessary to memorize all the properties or the formula of these distributions, but having an intuitive understanding of the distributions and about what they are doing and what does it mean, and having the probability to quickly derive the important probabilities of different distributions, as I think are quite important skills in practice. So let's first begin with the common function series. So for any random variable, we are going to have a cumulative distribution function, which basically is represented by the probability of x smaller than a certain value, a certain constant a. So this is going to describe the probability within a range of the left side. So for the discrete case, it is something like this, okay? If I talk this is A, right? And for continuous case, I just make it into a smooth line, and this is A. And then the probability mass function for the discrete case, or we call probability density function for the continuous case, is just one bar. It's just this one single bar for the discrete case, and for continuous case, then you can think it as one minimum divisible line within this area, okay? And then we are going to have the expected value. Basically, we are just multiply this probability x with x itself and sum them together or take the integration, okay? And then since we can take the expectation value of x itself, we can also take the expected value of any function which is constructed based on x. We just replace this x with the gx here. Okay, and then the variance is just the formula here, where after in the next lecture, when we're talking about the moments, we're going to know this is the second moment. And this is the square of the first moment. So basically, a moment is just x to t, and it is a tth moment, okay? And then we also have the standard deviation, which is just the square root of the variance x. So now let's start talking about some common discrete and continuous distributions. Let's first talking about the discrete side. We have 5 of them. The first one is uniform case, where x can be a plus 1, or b all the way to b. For example, for a dice, we can have x equal to 1, 2, all the way to 6, right? And the probability of each of them is what? Is 6 minus 1 plus 1 of 1 is 1 over 6, right? And the expected value is here, and this is a continuous variance. And for the binomial, so the binomial case looks quite similar with the combination number, right? We have a combinatorial here. But what does it mean? It basically means that within n trials, there are x wins and n minus x loss, and we win with p probability. Okay. And how about Poisson? When the first time I saw this distribution, I was quite confused because it looks so weird. It goes the exponential part, it goes the factorial. But basically, Poisson is quite important. Poisson is related with the first meetup, coming, all the things, all the natural coming problems. For example, the life length of a light bulb, or how long should I wait for the next taxi, all these things, the first meet problem, or the queuing problem are related with Poisson. And Poisson also strongly related with what? With exponential distribution. And exponential distribution is basically we're going to have exponential distribution family, which is a quite important part for the stochastic process in statistics. And how about the geometric? The geometric it basically means that x minus 1 losses before first success. So basically it's a probability, like for example, I need to fail 10 times until I get into Peking University, okay? And that's a probability. This P here is a probability that I get into the Peking University, assuming it's a constant. And the last one is negative binomial. So negative binomial is basically a general case of geometric distribution. Why? Because it is actually describing that you have R minus 1 win and N minus R loss before having the R swing. Okay. X, sorry, this is X here. So basically we can just replace this R minus 1 by 0, and this is going to be the geometric case, right? If we set R equal to 1. And it is actually quite similar, quite frequently seen in the whole distribution definitions. We can see some distributions are basically just the general case of another. It will become more obvious when I talk about the continuous distribution. For example, for the gamma case here, well, it looks quite complex, and it makes you worried that if I can understand it. But gamma is just what? It is just the general case of exponential distribution. And exponential distribution is trying to describe that the time we should wait between two occurrences of an event. For example, waiting time between two buses. Okay. And for beta, how about beta? Again, since it is named after beta, it must be something generalized. So beta can be reduced to uniform distribution. Okay, it's basically the general. It's basically the general distribution for uniform, and now you can see the uniform distribution here. We have both uniform distribution in discrete and continuous cases. And the only difference is that there is a +1 here, and there is no, and there is a +1 and -1 here, but we got none here. And the normal distribution, which is called the Gaussian distribution, and also the most important distribution in this world, right? Because a lot of things in this world is distributed in a normal way, right? We have most of the people here, a few are quite rich and a few are quite poor, and a lot of things have this kind of pattern. And this is exponential, I just mentioned. And how about if x follows exponential? Oh, sorry. How about if x follows normal? Then x squared will follows what? Will follows chi squared, okay? Will follows chi squared. And basically that's all the distribution you are going to meet for your undergraduate courses and for your master courses, I believe. Unless you are taking some PhD level advanced courses, you may count into some Bayesian distribution or something else, right? But those are quite less frequently to be used. So, and even they are used based on these foundational distributions I just introduced. So now let's come to the questions. So the first question today is called the meeting probability. So two bankers each arrive at the station at some random time between 5 a.m. and 6 a.m. The arrival time for either bank is uniformly distributed. They stay exactly 5 minutes and then leave. And what is the probability they will meet on a given day? So I'm going to introduce one more important principle here. So as long as this question is related with uniform distribution, then we can use plotting method. Okay, so we are going to use plotting method, or I can also call it geometric method. It is going to be quite intuitive and going to be fast enough to help you to solve the question, especially during the interview. And if you solve the question without using any formula but using plotting, you will give the impression to the interviewer that you are smart and you know how to solve the question in the most elegant and efficient way. Okay, and that's quite important in quant works. So let's see. So two banks will arrive at sometime between 5 and 6. So we are going to define this 1 hour. Let's say 0, 1, and this is the first bank. Let's just call it X, right? And we can see this is 5, this is 6. And I can define another bank will also be 0 to 1, and this is Y, right? And this, if they will meet on the given day, which means during the 5 minutes one bank stay, another one will come in, right? So if they always meet at the same time, and this is just a double line, Y equal to X. So it could move upward or downward for how many minutes? For 5 minutes, right? Because it doesn't matter if X comes first or Y comes first, as long as the other banker comes into comes to the station within the 5 minutes waiting time, right? So this is what? This is Y equal to X plus 5, and this is Y equal to X minus 5. And let's just draw a cube here, right? And this total shaded area is the probability they will meet on the given day. So we know the total area equals to 1, right? And how about this part? How about this part? This part is just 1 minus the triangle C, these two triangles. So for this triangle, it is, because it's 5 minutes, so it is just 5 over 60, which is equal to 1 over 12. So it is just 1 minus 2 multiplied by 1 over 2 multiplied by 11 over 12 multiplied by 11 over 12. And then solving that, it could gives us 144. And this is going to be 1 to 1, which gives us 23 left. And this is just the answer. Okay. But how about if we want to solve it in a more classic way, or I mean more, using the distribution definitions? So they follow a uniform distribution, and basically, so for X, I can take integration within 0 to 11 over 12, right? And the distribution is just Y here, the X, and how about Y? So for them to meet up, it must be within EY. Oh, sorry, I should. X is within 0 to 12, 11. And this is going to be X plus 5, X minus 5. Right, you see, if you want to use it this way, it's quite complex whether you should use 0 here or the other thing. And you can get any numbers, for example, like 14422 or 14424, because it's quite misleading. So if you are nervous enough during the interview, it is going to give you the wrong answer. So I don't suggest you to solve the question using the integration method, okay? And now let's go to the next question. So for the next question, it's the same. I'm going to see that as long as it is related with a uniform distribution, you can always solve this problem by plotting method. Okay, by plotting method. We do not need to take any integration. So a stick is cut twice randomly, which each cut point follows a uniform distribution. And what's the point and three segments can form a triangle? Again, since it's a uniform distribution, I just first defined a line which has length 1, right? Unit 1. And this is going to be cut twice. So we can have, this is, I just call it X, and let's call it Y. And this is just, let's call this part Y instead. Let's call this part Y instead. And then this is just a Y minus Y, right? Because they are going to form a triangle, and we know for a triangle, any two lines of a triangle, the sum of them should be larger than the another line left, right? So we can have what? We can have X plus Y minus X should be larger than 1 minus Y, and Y minus X plus Y minus Y should be larger than X. And also 1 minus Y plus X should be larger than Y minus X. And for this one, we can get Y larger than 1/2. And for this one, we can get X is smaller than 1/2. And for this one, we can have 1/2 plus X smaller than Y, right? And for all of these things, I can now draw a picture. So again, this is 0, 1, 0, 1, and this is X, this is Y, right? The range of X and Y is within 0 to 1. And I know X is smaller than 1/2. And Y is larger than 1/2. So we already only have this range left. And then we also need to have that Y is less than X plus 1/2. So this is Y equal to X, right? Plus 1/2, so we are going to have this line, and Y is less than that, so this part. And the total area is what? Is 1/8, right? It is 1/8. So now let's go to the next question. But, oh, sorry. Actually, the result is not just 1/8. This is wrong, okay? This should be 1/4. Why is that the case? Which part did I miss? The point is that X can, I already assume that Y is larger than X, but it can also be the case that X is larger than Y. And if that is the case, we can also have another shaded part, which is this area, okay? So we are going to have 2 multiplied by 1/8 equal to 1/4. Okay, sorry for that. So we need to be quite careful when it comes to the uniform cases. We need to do all the surrounding discussion, okay? So now let's come to the next question. The next question is, compared with the question, I'd rather call it a revision for the property of Poisson process. So I'm waiting for a bus at the bus station, which is a classic example for Poisson distribution. And the buses arrive at the station according to a Poisson process with an average arrival time of 10 minutes. And then if the buses have been running for a long time and you arrive at the bus station at a random time, okay, then what is the expected waiting time? And on average, how many minutes ago did the last bus leave? So let's first solve the first part, okay? This is the first part and this is the second part. Let's first solve the first part. So basically, it's just the definition of the exponential distribution. So this whole process, have a bus, it's called what? It's called jump diffusion process. So exponential distribution, where ft equal to 0, lambda e negative lambda t, as long as t is larger than 0, t smaller than 0, is going to describe this process. So you have something which is going to follow a Poisson, which the bus is going to arrive according to a Poisson process with an average arrival time of 10 minutes. So then this lambda is going to be 1/10, right? Which is 0.1. In that case, the Poisson, the exponential distribution with the same lambda. So this is just a 0.1. Let's use 0.1 here. E negative 0.1 t is going to tell us the average waiting time. And the expected waiting time is just expected t, which is just 1/lambda is 10 minutes. Okay. And for the second part of the question, it is related with an important rule, which is called memorylessness. Okay. So if we write in statistical language, it means what? It means if there is tau, we are going to calculate the probability of a tau, which is larger than s plus t, conditional on tau is larger than s. It is going to be the same with probability tau larger than t, which means this s part could be forgotten. If we have waited for s time units, then the extra waiting time will have the same distribution as the waiting time when we start at time 0. Well, it is quite counterintuitive, but it is true. The reason is that when you arrive at a bus station, the probability that you need to wait longer than the average time is higher than the probability you're waiting shorter, because the expected time should be on average the same. Okay. And so in this case, let's go back to the core problem. On average, how many minutes ago did the last bus leave? So basically, we are asking what? Probability, the expected time of the expected time of arrival of the last bus, right? And according to the memorylessness probability, it is going to be same as our expected waiting time for the next bus. So again, it is going to be 10 minutes as well. Oh, I like this, the color of the pencil. I should use this one more, okay? Maybe, yeah. So let's come to the next one. The last one is the not the last one. So the next one is about the moments of normal distribution. And if x follows standard normal distribution, what is EXN? Basically, it is asking for the first to the fourth moments. And what are these of these? It is related, this one is related with mean. This is related with variance. And how about the third one? The third one is related with the skewness. It is right skewed or left skewed. And the last one, it is going to be related with the curvature. And this is related with the tail analysis, okay? Because it is going to enlarge the impact of those tail points. And for this one, it is going to enlarge the impact of the directions. And for these two are already quite familiar, right? So let's first define the moment generation function. So MT is basically equal to the expectation of ETX, which is just equals to discrete case and continuous case. In discrete case, it's just the sum of ETX probability X. And this one is just the integration of ETX fx dx. So why this one is called the moment generation function? Because we can see if we take the first derivative of this MT, then this is going to be E, because we are taking derivative according to T. So X is the parameter. So this one is going to be X ETX. And then if we set it to 0, then this 0 is going to be EX. And again, if we take the third search derivative, then it is going to be EX the cube and ETX. And when we set the T to 0, it is going to be just EX to the power of 3, right? And it is going to give us the error moment because each time we are taking one X downside down to the parameter. So we can use this probability to solve the EXN for the normal distribution, right? And I'm going to just tell you the answer here. So for N01, MT is just equal to ET squared and divided by 2. And if you have good memory, I hope you could remember this one. Because sometimes if we see something, we see this format, for example, we see this EX squared. One of the way to solve that kind of problem, we are going to meet some of the problems in later chapters, is to consider this as the moment generation function and to solve it by some properties of a normal distribution. And that is going to be a super smart way to solve certain questions. Yeah, if you know that and you show that to your interviewer, it's going to give you some bonus marks, definitely. Okay. And now let's come to today's last question. It's some random variables. So assume that x1, x2, and xn, we have n variables. They are in the ID, independent and identically distributed random variables with uniform distribution between 0 and 1. So what is the probability that Sn equal to x1 plus x2 plus all the way to xn smaller than 1, smaller or equal to 1? Again, according to our uniform distribution rule, what kind of method should we take? We should use the geometric, we should use in the plotting method, right? But you may ask, right, hey, Alan, we are getting like a lot of sums here. We cannot write like an n-dimensional cube or n-dimensional square, right? But again, let's just start. Let's combine it with another simple rule is that we start with a simple case. For example, n equal to 2, right? And then the probability is equal to what? Xn plus x2, x1 plus x2 less than or equal to 1. And this is just going to be the cases here, right? This is Sn equal to x1 plus x2 less than equal to 1. And this is what? This is n equal to 3 cases where it is equal to x1 plus x2 plus x3 less than or equal to 1. You can see this is a triangle, and this is somehow triangular, okay? So this area is easily to be calculated. We can see this one is 1/2. And how about this one? This one is just the volume. We can see this part is 1 multiplied by 1 multiplied by 1/2. And this one is just 1 multiplied by 1. And since it is a triangular, so this is going to be so since this is a cone, okay, this one is a cone, so we need to multiply that another 1/3, and this is giving us 1/6. But let's stop here. Let's stop here. Sometimes you do not want to solve this question too fast, right? This is what? This is 1/3 multiplied by 1/2 multiplied by 1, which is just 1/3 factorial. And this is what? This is 1/2 factorial. So we may guess, right, that the solution P Sn less than 1 is going to be 1/n factorial. And to prove that, we can use what? We can use mass induction, right? We can use mass induction. But in interview, I think as long as you can get this answer and using a plotting method, they are going to let you go. But now I'm going to solve this question in a strict proof. So we need to prove that probability Sn plus 1 less than 1 is going to be 1n plus 1 factorial, right? And how can we solve that? First, we change it into the integration. This is going to be 0 to 1, right? And this is fxn plus 1 probability Sn equal to 1 minus xn plus 1. Because we already know that Sn is going to be smaller than 1, then as if we have a distribution of xn plus 1, then the left n should be smaller than this part, okay? And this is dxn plus 1. And this is easy because we know each x follows a uniform 0, 1. So this one is just 1 over 1 because it's b minus a, right? This is going to be 1. So we just need to take care about this part. For this part, because now we are thinking this as originally we are comparing Sn less than or equal to 1. And 1 is the length of the signed length of the square or the cube. We just need to replace the length of this line from 1 to 1. 1 minus xn plus 1, right? Which means I can think this 1 over n factorial as 1's factorial over n's factorial. And now this becomes what? 1 minus xn plus 1's factorial over n's factorial, right? And since I'm going to multiply it n times, this is going to be n, okay? And then it becomes 0, 1, and this part, dxn plus 1. So this is going to be 1 over, let's just take the n factorial out. And this is going to be negative 1 minus xn plus 1 to the power of n plus 1 divided by n plus 1, right? And conditional on the rank 1, 0. And this is going to give us 1 n's factorial multiplied by 1 over n plus 1, which gives us 1 over n plus 1 factorial. And we proved that the probability of Sn less than or equal to 1 is going to be 1 over s factorial. And so this is going to be all the questions for today's lecture. Thank you for watching and see you next time. Next time, we're going to talk about the expectation, variance, and all the statistics. And it is going to be the last lecture for the probability theory chapter. Okay, thank you.